All right, we're on the air.
Great. I don't know Matt's official title, but he is a executive at Pilosa, and he's going to talk to us about his distributed uh, data structure that they have built, which I think is actually really, really interesting to this community in particular because of its potential application to store data that might be useful for people who want to collect information about customers and target things to customers very particularly. That's one of the use cases that I know he's talked a lot about. So Kroger, P&G, places like that that are very interesting clients in the area. And Matt, I met Matt 2 years ago at GopherCon, and he has done a lot of really, really, really interesting work at Pilosa. And I'm very excited to hear what he has to say about how they use Go and how they get it to work in such a high performance data structure. And I really, really, really have been looking forward to this, and I appreciate him taking the time to set this up for us. So I'll let him carry on from here. He can hear us. We can obviously hear him. So if there's questions or anything, I'll let him dictate the terms for those questions. But we'll go from there. So thanks, Matt.
You see it's okay?
I think I can see most everybody. I see 5 people. Will just walked out of frame. Yeah, questions are definitely welcome at any time. I've talked about Pilosa many times, but this set of slides is totally fresh. So any feedback is definitely welcome. I guess, first of all, has everyone voted?
I'm not registered.
Okay, because if you haven't, go vote, and I will give you this talk privately another time. I promise. With that said, so I'm going to share my screen, which means unfortunately I can't also share video. I tried a couple ways of getting that to work and my computer was falling apart. But I will still be able to see you and hear you. So if you have questions, you know, speak up, raise your hand, whatever. But yeah, let's jump in. All right, does that come up? Everybody see that? Cool. All right, so Pilosa, thanks, Will, for the introduction. Did a pretty good job, except I'm not an executive. Sorry to disappoint anyone, but I am a engineer, back-end engineer, and hopefully that will be a better fit for this audience anyway. Couple businessy slides first. I think we can all agree that the amount of data that people are storing and needing to access is growing quickly, probably exponentially, and not just business data, but you know, sensor data, IoT data, stuff like oil platforms produce an enormous amount of data. Human data, you know, human genomes are gigantic, and we've barely scratched the surface of you know, what's possible to do with that kind of data. And right now, it's the sort of state of technology is that we make a lot of compromises in order to be able to access data and report on it. And so, you know, we do caching and data is stale, or we batch things up, or we do aggregations, sampling, deresolving, or just like we wait a long time for queries to run. You know, we say it's okay if we get that report next month or next week or whatever. And I think, no, that's not okay. And that's kind of our thesis at Pilosa, is that being able to access data quickly and get the results you need and do the analyses that you want to be able to do and explore your data is going to be a key competitive advantage for pretty much all businesses, you know, for the next foreseeable future. So what is Pilosa? Well, it's an index. So like Elasticsearch? Well, kind of. Elasticsearch is an index in that it's not meant to be your primary data store, but it still stores all of your data, you know, pretty much in a straightforward way, and does some indexing on top of it. And I want to sort of try to explain how I think Pilosa is fundamentally a little bit different from what Elasticsearch does, and why that's powerful. So typical database might store your data like this, where you've got, things laid out logically, and this is an abstraction, but it's also generally how a database stores your data. It's lined up in these rows, and each record is stored with all the fields of itself. Pilosa looks more like this. And so some of you, your mind may be jumping to columnar store, and that's basically entirely correct. But in Pilosa, everything is built around bitmaps. And so let's see, can you see my mouse? What if I like highlight? Oh, that's just going through the slides. All right, never mind. All right, so each bit or unset, each 1 or 0 here represents a bit that's either set or not. And this particular bit that's highlighted now is saying that person 3, who in this case is Grace, is from country 1, right? And this is how bitmap indexes work in all kinds of technologies, from relational databases to, I mean, even Elasticsearch uses them. And it's basically you just break out your column into all of its values, and then each value gets a bitmap that says which records are actually associated with that column. So a query in Pilosa might be, oh, give me, the set of people who live in the United States. And then the return of that query is just a bitmap. And you could say, oh, just give me the count, and then it will count the number of set bits. And so that's all like pretty well compressed and very fast. A slightly more complicated query might be, well, I want all of the engineers who live in the US. And so that would actually be a logical AND of 2 bitmaps, giving you a resultant bitmap, which is all the engineers who live in the US. And because the result is still a bitmap, you can continue to combine that with other filters. You could say, or, the people named Ada or Margaret, and on and on and on. You can sort of continually add more to these filters, and the results are always still bitmaps. The other cool thing about that you don't really get a sense of from this slide is that you're probably going to have millions or billions of columns, right? And columns in this case, the way we've laid the data out, are the actual records. So you're probably going to have millions or billions of person records, right? And these logical operations can actually be performed concurrently by, tens or hundreds or thousands of processor cores by splitting up, just along records. So not only is it, ridiculously fast to do a logical AND on a bitmap, in your CPU, but you can split up the problem across as many cores as you want, basically. So Pilosa is a bitmap index. And yeah, maybe that could just be like a library that you use. But that's not a question. And it's also not quite correct, because remember, we're talking about like huge amounts of data, terabytes, petabytes, whatever comes after petabytes, massive quantities of data. And so Pilosa is not just a bitmap indexing library, although it contains that. It is a distributed bitmap index, and it is written entirely in Go. And you can actually just import the library part of it if you wanted to do that. We've been pretty heavy adopters of dependency injection and being very careful about not depending on things in core Pilosa and sort of injecting them as modules. And so you can swap things out very easily. And that is actually the subject of another talk that is pretty interesting. But I wanted to go over the sort of core of Pilosa and how it works, especially given that, Will told me that this audience would probably be into it. So it's just a distributed bitmap index. Here I've split out one column onto each node, which is obviously not realistic. You would probably have 10 million columns on each node or something. The salient thing to notice here is that that mapping of what row goes to which value for each particular field is on every node. And so every node can sort of do that translation if it needs to. And we'll talk about why that's not too terrible in terms of storage in a little bit.
Hey, Matt, I think we had a question here before you go on.
Sorry?
We had a question here before you go on.
Yeah.
So I noticed that these variables are discrete. What happens if you have ones that are continuous? For instance, I'm doing a lot of stuff right now, networking multiplayer clients in a 3D environment, and the positions can be something like 8 decimal points long. So what do you do about things where the value for a certain variable can't really be like discrete number?
So you'll notice I actually, I had, where is it? I had this age thing on this slide, which I didn't really talk about, and I'm going to get to that later. But we've also done things like we ingested the sort of the billion taxi ride data set. Are you familiar with that at all?
No.
A few years ago, this data set of over 1 billion taxi rides in New York was released. And so we ingested that, and we actually mapped all of New York onto like a, I don't know, it was like 100-foot by 100-foot grid squares. And then we stored each grid square as a separate bitmap in Pilosa, and we were able to get kind of cool histograms and visualizations of like where these taxi rides are mostly going from and coming to for different segments. So like spatial data is not directly supported in Pilosa, probably will be one day, but there are definitely some cool things you can do with that. I will talk about sort of how to deal with larger integers a little bit later, and floating point is not something we support right now, but hopefully will in the future, and I can talk about that a little bit too. Does that?
Yeah, that's good.
Hopefully this will become a little bit more clear as we go on. Distributed bitmap index, so lots and lots of nodes, potentially lots and lots of shards on each node, because each node, you know, probably has many CPU cores, and each one can process, you know, lots of shards. Each one can process a shard or many shards concurrently. And so it's actually worth mentioning there are use cases where you might have a very low query workload, and so you want each query to perform as quickly as possible, and so you just want to have one CPU core per shard of your data. But then there's also workloads where you might have very high query concurrency, and you actually want to allocate more than one CPU core per shard of data so that you can handle multiple concurrent queries. So the next question is, you know, when you're storing things as bitmaps, doesn't that take up a lot of space?
Can you go back to your slides?
Yeah. Sorry, which one?
Just go back. No, we aren't seeing your slides. We're seeing you right now.
Oh, I'm so sorry. It's going to take me a while to get used to this. Present.
Perfect.
Right. All right. You didn't mention much. So lots of nodes with multiple shards on each node. And then doesn't this use a lot of memory and or storage? And it can, but there's a few reasons why it's actually pretty good. So that looks like a lot. More than that. But remember that we don't actually have to store all these indexes. Those are kind of implicit. And so that visually kind of pares it down a little bit. And then if you look at these lookup tables, they tend to grow sublinearly, right? So if you have like 1 billion people in your index and you add 1 billion more, you're probably not going to get that many new occupations or new countries, right? Like the number of countries is pretty well fixed. And so those things tend to grow much more slowly than the actual number of records, which lets it scale out pretty large, despite the fact that we are storing that mapping on every node. And then because of that, each new record in sort of the common case is just twiddling, a few bits across its different fields. And so it is, it's adding that whole fourth column, but the 0 bits are implied, basically. If you're going along adding columns, you don't actually need to do any work to add that 0 bit. It's just the 1 bit that you need to actually change some data. So this is pretty interesting because it means that Pilosa can both ingest data quickly and serve analytical queries very quickly. That's not to say that it's like a silver bullet, because it's really not good at like transaction processing type workloads where you just need to do like a point lookup, like look up a single record. That's super slow in Pilosa because the data is scattered all over the place. You have to look it up in like 6 different places. But in terms of analytical processing, typically you're trading write speed for read speed. And in Pilosa, that's not necessarily the case. Okay, so this bitmap thing, it still seems pretty expensive if you have 1 billion records, which is, a lot, but not that much. And you have a field that's name, and it has 1 million possibilities. Its cardinality is 1 million. That means you have 1 million bitmaps by 1 billion records, which comes out to like 125 terabytes. And to that, I say, roar! So there's this really awesome compression format called roaring bitmaps. And this is the product of several decades of research into bitmap compression and processing. And it's really like amazingly simple compared to a lot of the previous stuff, which uses all kinds of wacky compression techniques. And it basically just says, if your data is sparse, we'll just store an array of integers that represents the set of numbers that the bitmap represents. And if the data is very dense, we'll run length encode it. And so we'll say like, the bits are set from 1 to 57 and 99 to 144 and so on. And so that compresses it down a lot. But if the data is very high entropy, we'll just store it as a bitmap because that's really, really fast to process. And then the absolute key thing about roaring bitmaps is that every operation, whether it's logical AND, logical OR, XOR, difference, is defined for every combination of those 2 or of those 3 compression types. So we actually have a method in Pilosa for intersecting, doing a logical AND on a bitmap encoded container and a run length encoded container, and a bitmap encoded container and array encoded container, and a bitmap with a bitmap, and so on and so forth for every operation. So there's definitely somewhat of an explosion of the number of things you have to implement. But once that's done, and it's a few thousand lines of code, you don't really have to touch it anymore. Mod some optimizations and hopefully not too many bug fixes. So roaring is really cool in that way. It's also very cache friendly, the way it's kind of laid out. And it just ends up being really, really fast and getting pretty good compression ratios as well. We actually modified roaring slightly because the original spec was for 32-bit integers, and that would basically limit us to 4 billion records or less. And we're designing for big data scale, modern era, or whatever. We want to be able to support tens of billions, trillions of records potentially. So I love this quote. The roaring bitmap people have it on their site. Use roaring for bitmap compression whenever possible. Do not use other bitmap compression methods. It's from this very prestigious database conference. Actually, I found this similar quote about Pilosa as well, which I really like.
It's a pretty prestigious conference.
Yeah, it's super prestigious. All right, so how big do these compressed indices actually end up? 125 terabytes is a large pill to swallow. And it's like, you can't just tell someone how big it's going to be a priori, because it depends on the layout of the data and all this stuff. And, but people will press you on this. And it's really hard to try to, all right, yeah, okay. So usually it's like between a fifth and a tenth of the size of the raw data. And so like that billion taxi ride data set was 300 gigabytes raw. And then it went down to like, I think it was like 40 or 50 gigabytes of Pilosa indexes. So that's pretty cool. And we were actually a little bit surprised by that. But up to this point, we've basically just talked about where clauses. If you're familiar with SQL, doing segmentation, saying, I want all the records that have this or this, but not this. What else can Pilosa do? So I promised we'd talk about integers, and I guess my integer friend just walked away.
No, he just moved.
I need a background.
Yeah.
Okay. So integer data is handled a little bit differently. We actually encode the binary representation of the integer across multiple bitmaps. And it turns out, so that's the binary representation for 102. It turns out that you can actually generate arbitrary range queries across the data. So I can say, give me all records which are, have ages between 25 and 34. And you can generate a query, which is a sequence of, intersections or unions or differences on these bitmaps to figure out what the bitmap is that represents all the records that have an age between 25 and 34. And so just a really simple example would be, give me all the records that have age over 32. Oh, well, if they have a bit set in 2 to the 5, 2 to the 6, or 2 to the 7, they're over 32, and otherwise they can't be. So that's just a logical OR of 3 bitmaps. And then we intersect every query with the existence bitmap so that we can tell the difference between records which are 0 and records which are null, basically. All right, but that we still are really in where clause territory here. Let's talk about top N queries and group by queries. So what are the top 10 occupations in our data? Pilosa actually keeps a little ranked cache alongside the bitmap data for each field so that you can do queries like this. And so as the data gets updated, we update the ranked cache on a per shard basis, so it still scales. And we know the count, basically the number of set bits in the bitmap for each thing, and we keep this ranking of their order. And so we can do a top N query and say, what are the top occupations, or what are the top countries that people live in our data set. And so that's cool. It lets you get like a histogram view of the data very quickly. But where it really becomes powerful is when you combine it with, I forgot to update the title on that slide, with arbitrary filters, these segmentation filters. And so you can say top occupations among certain ages, or top occupations among people with these 3 names and these ages. And you can basically pass in as complex of a filter as you want. And so that allows what is more or less group by on a single field with an order and a very complicated where clause. And we actually support group by over multiple fields as well. And that's a very recent change that we just merged. And the code for it was hairier than I was expecting, but it works. It's pretty cool. And we can actually paginate through that because sometimes those result sets get pretty huge. And so you can say, group by country occupation, that would give you a list of how many engineers are in the US, how many mathematicians are in the US, how many doctors are in the US, et cetera, and the counts of each. All right, so what else can it do? How about we add the ability to give a timestamp on every set bit? So this is pretty interesting. When you set a bit, maybe you're setting a bit that says somebody opened an email, but you also want to be able to say, okay, they opened the email on Wednesday at about 4 o'clock. And Pilosa has this support for coarse-grained timestamps that apply to single bits. And so the way it's supported, it actually sets several bits. It doesn't just store the timestamp along with the bit. Everything has to be a bitmap, remember. So it will set a bit for the year, and then the year and the month, and then the year and the month and the day, and then the year and the month and the day and the hour, if you go down to hour. You can also go to coarser granularity if you want to be a little bit faster and save some space. So what that lets you do is, build arbitrary time range queries across your other filtration queries. So you can say, I want all the people that are between these ages and live in this state and open this email, within 2 days of it going out, or the ones that opened it, later. So there's sort of lots of interesting potential applications for that. And it's still quite performant because you are still just setting a few bits for each of those values.
Now, Matt, in that case, do I have to have a row for each thing that I potentially want to agree on? So I would need, if I only want to break it down by year and I've got 40 years of data, I would need a 2017 row, 2018 row, and a 2019 row.
Sorry, it's a little bit tough to understand.
Sorry. So if I wanted to do a query for just like who opened it in what year, I had 3 years of data. I would need a 2017 row, and if I wanted it by year and month, I would need a 2017 row.
Yeah, right. But Pilosa actually does that automatically. So you would just say, set the bit that says this person, opened this email and with this timestamp. And Pilosa would say, okay, I'm going to set a bit. Behind the scenes, it actually maintains several different files that have opened email 2017, opened email 2017-01.
Saying is that seems to break some of your pieces that those data types and the data values goes some linear. That's a lot. It goes linear.
It definitely uses more space. Now I have to think about this.
The second I have a year, the second for another year, then that's twice as much.
Right. So as time goes on, that one will continue to grow, but not necessarily as the amount of data that you're ingesting grows.
If you need to have one field is the year, and then the rest of the field is month, day, hour. Couldn't you just actually have that one extra year literally? Like for each year you have a column, and then for each month you have a column. Every time you add an extra year or an extra anything, extra month, you're only adding. You don't need to track like January 1st at 3 p.m. You just say it's January 1st.
I'm sorry, I'm catching every third word.
That's right, we're good. We're good.
I'm having trouble parsing.
Is that a good enough solution?
Thanks, Matt. You can keep going. I'm sorry.
It might work if when people want to ask questions, just come up closer to the computer.
Yeah, sure.
because I do want to answer as many questions as I can. So actually, I think that's the end of my Pilosa slides. I was going to move into some, why we use Go. Oh no, I got a roadmap slide. So we actually talked about a little bit of this. Floating point support, text indexing.
Again,
Matt. I'll figure this out. There we go. Roadmap. Floating point text indexing. So that's would be, it could be full text indexing, or it could be supporting things like queries, where we might do some indexing on the row values so that you can grab certain sets of rows more flexibly, certain sets of attributes. And there's a variety of ways you can do that with a bitmap index. Whether it's like taking out bigrams or n-grams and indexing text documents that way. And we've experimented with some of that stuff a little bit, but haven't really had time to dig in. We would like to support a SQL-like query language, and we're kind of getting there with some of these features like group by and such. But then we actually do have to plug the SQL front end into that. Time series data, distinct from the timestamps we just talked about, but actually being able to associate a fine-grained timestamp with each record that comes in. And so you're basically have records coming in, you're allocating new columns, storing the record, and then potentially aging them off as well. But it should be pretty performant to be able to query over certain time ranges of whole records, not just set bits. And I think we can support that fairly easily, which might open up some cool like IoT use cases. So more streaming integrations. We have a pretty good Kafka integration right now, but we want to be able to ingest data from lots of different sources very easily. And then there's, sorry? There's a variety of like weird use cases that we want to dive into that we just haven't had time to. But I mean, most of what I've talked about today is like the standard sort of analytical SQL-like use case. But we were doing stuff where you just take a whole human genome. It's like 3 billion bits or something, and you encode it in a single bitmap in Pilosa, and you do a whole bunch of those, a bunch of different people, and then you can really quickly do comparisons between the people. Like, all right, how many base pairs, do these two people have in common or not have in common? Or you like mask off certain chromosomes or certain regions and say like, what do these people have in common in this region? Who are the most closely related people to this person who has, this certain disease? I think there's a lot of potential there, and the performance is just absolutely stupid, especially compared to like a lot of the current tools in that space are built by, very intelligent scientists who are not software engineers. And so, they're like written in Python or whatever. So I would love to get more into that, because I think there could be a huge impact there. Plugins. So sort of being able to define your own algorithms for sifting through data and iterating on it on the cluster. We did an interesting thing a few years ago where we searched for biclicks in a graph. And so it was like, just clusters of related data. There's an algorithm for doing this that, probably would be difficult to express in a query language, but we were able to sort of search through our user data with its attributes to find groups of related people who had similar interests, which is a fairly, it's an extremely compute intensive problem, especially on lots of data. And so being able to easily parallelize that and do it on compressed bitmap data rather than raw data should, in theory, provide a significant boost in performance and open up some interesting use cases. And then, of course, it's open source, so please, submit new issues and tell us what we're missing. So let's talk a little bit about Go. This is the Go meetup after all. Pilosa's written in Go. We've all written a ton of Go and debugged a ton of Go and optimized a ton of Go. So why did we choose Go in the first place? I don't know if we chose it in the first place for sanity, but I think that's probably the best reason to do it. My favorite thing about Go is that it's such a small language and is, it's easy to learn. It's easy to read. You have to try pretty hard to make your Go unreadable. I think you'll all agree. And that has been incredibly helpful in allowing us to, build a fairly large, complicated code base. Why we originally chose it probably had more to do with the concurrency support and the performance, which, as far as the concurrency goes, I think, that's almost second to none. Being able to have a single query, peg every core in a cluster of machines that have, 36 cores or something is really fun. And you get, pretty incredible latency numbers on really complicated queries. So I do love Go's concurrency model. I think it's the right one. Deployability, I'm sure most of you are operationally familiar with Go, and it being easy to deploy is a huge bonus for us, especially since our main competitors are things like Druid, which are written in Java and have like 12 dependencies. Like you have to stand up Zookeeper, and oh, you need a MySQL running over here, and there's like 3 different node types. And so, even just running a very basic Druid is like 7 services that you have to have going. And Pilosa is one that you just get a binary and you run it on a couple servers. And we have Go to thank for that. It also, it lets us do funny low-level stuff when we need to. We try not to do much of that. Before the math bits package got merged into Go, we had a little bit of assembly for doing stuff like counting the number of set bits in a uint64 or something like that. And we use a little bit of unsafe to do mmap because we keep all the bitmaps in memory mapped files. And that allows us to recover quickly if a node crashes because everything's on disk, but also operate quickly for queries. And Go's performance is good, and sanity. So Pilosa is effectively a database. We call it an index for marketing purposes, but for engineering purposes, we have to do most of the stuff that database people have to do. But I was actually doing a lot of research on real databases recently as we're trying to support more SQL, and I found that a lot of these papers have whole sections that we just don't even have to think about because we use Go. And so one of my favorites was this. It's actually a book by Hellerstein, Stonebreaker, and Hamilton. So these are some titans of the database community that have been researching this stuff for decades. And they have this section on like multi-core processing and stuff. And it's like the first sentence is, when designing any multi-user server, early decisions need to be made regarding the execution of concurrent user requests and how these are mapped to operating system processes or threads. Check that one off. Thanks, Go. Right, the runtime it does it for us. It's all done. And net HTTP takes care of concurrent requests. Right, it's amazing. So there's massive swaths of problems that we didn't have to deal with because of Go. I guess I'd be remiss if I didn't talk a little bit about why you probably shouldn't use Go to write like a database. And there are definitely a few reasons. There's probably a few more than this, but I'm pretty biased. Writing anything performance sensitive in a garbage collected language is always going to be contentious. Go's garbage collector is pretty well tuned for low latency, especially compared to like Java, which is another reason to use Pilosa instead of Druid. But it is still garbage collected, which adds quite a bit of overhead. There's tons of ways to sidestep the garbage collector, but they all mess your code up pretty badly. Well, not all of them, but once you kind of get past the basic stuff, you're definitely in some dangerous territory. And so removing, allocations from hot paths is a great way to optimize, but having to do it in the first place, is something that you have to be wary of when you have a garbage collected language. And you're never going to have the same kind of consistency of latency that you would with a non-garbage collected language. There's also the issue of generics, right? Like there's some instances where you want to write some code that would be much prettier with generics and just ends up being verbose and kind of ugly in Go, especially around like processing like the query language and dealing with lots of different data types or result types. Things can get kind of messy, and then in ways that they don't really need to be. I'm not really asking for generics in Go, though. I think the pain is often worth it, mostly because I don't want to see a bunch of generics in other people's code where they don't actually need them. That's the beauty of Go, right? Like other people can't write terrible code. And the compiler is still not incredibly mature, right? There's a lot of optimizations that the compiler could do, and that it probably will in the future that it doesn't now. And so there's places where there's extraneous bounds checks that really slow down your code. And, you still see compute intensive workloads are still like twice as fast in C or in C++ than in Go. But 2x is really not that much compared to, like Python versus Go is like 50x or something. It's ridiculous. So I did this quick slide on tips for high performance Go. Some of you or most of you probably know most of these, but the biggest one is just hang out in the performance channel and go for Slack, because there are some really smart people in there. Avoiding allocations and profiling are the next two biggest ones. I mean, profiling is definitely your first step anytime, and Go's profiling tools, if you haven't used them, are fantastic. You can get a ton of cool information, not only about what the CPU is doing, but how you're using memory, where things are blocking on mutexes or channels, or Go has a lot of good profiling tools, and it has the tracer, which gives you like every ounce of what your program is doing, like every move it makes, although it's significantly more overhead. So that stuff's all really cool. I think I'm basically done. Does anyone have questions?
You said it was distributed. Can you talk a little bit about like how that works? I assume it's, I don't know if you use Cassandra or anything like that, but like, is it distributed in the same type of sense where like you just query it and it will just pick a node type of thing, or how does that work?
Yeah, it is actually pretty similar to Cassandra. So we use this library called MemberList that actually came out of HashiCorp. The people who wrote Vagrant and just got acquired, or they didn't just get acquired, they just got a huge round of funding at a 1.9 billion valuation, I think. But so the nodes do gossip amongst themselves. Right now, you sort of statically assign a coordinator, which doesn't get used much except for when the cluster needs to be resized. But basically, all nodes are equal in the cluster, and when you do a query, most queries need to get branched out to every node because the data is spread out across all nodes, and so that's how you get super fast query processing is they process across all the data on the whole cluster. For ingestion of data, that will get directed to whichever node is supposed to hold the shard that you're currently ingesting to. Yeah, I mean, basically the cluster maintains membership. The nodes maintain membership amongst themselves, and you can add new nodes and it'll sort of rebalance the data, and it decides where a given piece of data goes using consistent hashing. Did that answer that, or?
Yeah. Anybody else?
I asked my question during the presentation.
Oh, I don't really have a question. It's a question, like, so you mentioned about the garbage collector, right? And have you tried to disable the garbage collector playing with Pilosa? I don't know if it's clear what I said.
Nah, you're gonna have to come up. It's really like every third word.
Hi. First of all, thank you for the talk. I really enjoyed the talk. And my question would be, have you tried to disable the garbage collector at all? Because Go 1.7 or 1.8, they made this like available.
We haven't. I had one sort of weird performance issue I was looking at where I was thinking I might disable it and just see if it kind of went away. But it was not high on my list, and I never got around to doing it. But yeah, we haven't actually experimented with that. And I mean, we do enough allocation that it would crash the node eventually. I mean, in not infinity time. So it's definitely not a long-term option. But it would be kind of interesting to see what sort of how much more consistent our latencies were, with that turned off. It's definitely something that would be worth doing.
Yeah, like I saw like the code, like how to disable, and it's basically like one little argument that you pass for the compiler. Just out of curiosity.
Yeah, definitely. It's not like it's hard to do. Like many things in Go, cross compiling and all kinds of stuff is just setting environment variables.
Yeah. Oh, cool. Yeah, I really enjoyed this because I work actually with genomic data, sequencing data. And,
oh, really?
Yeah, and it's interesting to see like use case like that where you compress like data and like you make queries like faster. Like, so I always find it interesting.
Yeah, we have a blog post on that actually. Let me see if I can put that up. All right, here we go. So you can see. And...
Oh, okay.
Yeah, so we kind of talked about the approach we took in Pilosa. And I mean, none of this stuff is like super production ready or anything, but it was really interesting to see, what the performance was like. And the way that we laid this data out is the absolute best case for ingestion into Pilosa. So we were able to, ingest whole genomes in like a few milliseconds. It was pretty nuts.
Yeah, like one file for a whole genome or sequencing data is like gigabytes something. It's very interesting. All right. Thank you so much, Matt.
Yeah, no, thank you for coming.
Yeah.
Question about parallel processing, and it seems like you have many. You mentioned you do a query, you scan, or you do a comparison against all data across all nodes. I'm wondering how you tune for performance, based on the CPU capacity of the host operating system, how many operations do you run in parallel? How many coroutines do you run that are doing those queries?
So basically, we launch a Go routine per shard. And so a shard is by default 1,000,000 records. And in a typical deployment, so like when we did the taxi data, that's about 1,000 shards because it's 1,000,000,000 taxi rides. And we would do that on like, you can do it on any size cluster you like, but we did it on a 3-node cluster where each node had 36 cores. And so the query gets fanned out, and each node will launch approximately 300 Go routines to process that query. And we just let the Go runtime decide how to schedule those Go routines, and process each shard. And then once they're all done, there's like a pretty simple reduce step to basically add the results of each together, and then that gets sent back to the client.
So since you have one Go routine per shard, I mentioned you're limiting the number of blocks or current checks, making to merge that data back together.
Yeah, because all the shards are pretty much independent. They're in separate files on disk, so there's not much contention between them once the query gets fanned out.
And so you're handling some of that contention by dedicating a coroutine to shard.
Right. Yeah. I mean, it lines up with the way the data is laid out. That's actually something I think that probably doesn't see as much discussion as it should, but how to best when to spawn a Go routine versus not, or how to parallelize things in Go routines. And I can't claim credit for the decision we made to kind of do it the way we did, but I think lining up your Go routines with pretty large blocks of data and keeping the number fairly small. I mean, Go will handle tens of thousands or hundreds of thousands of routines, but it's definitely better, easier on the scheduler and everything if you have a few hundred or less.
And my other question is also about performance, and that's what kind of indexing rates or indexing latency can you achieve, and how do you determine how to allocate hardware or spec out hardware based on the size of your data set or the nature of your data? I know it's a pretty complicated question, but
yeah, no, it's a good question, and it's one we're trying to get better answers to through more rigorous benchmarking. But basically, you can get kind of a feel for the size of your data by looking at the raw data and looking at the cardinality of each field, and that's like the main driver. To some degree, also how it's laid out, but cardinality is really big, and so you can get a pretty good feel for how much memory you need. And we typically tell people to use fewer bigger nodes rather than many small nodes, just because there's less network overhead and that kind of thing. But we really need to benchmark more to sort of validate that recommendation. As far as ingest speeds, it again is going to depend a lot on your particular use case. Like I said, with the genome thing, we were basically able to ingest into every shard simultaneously. And so all nodes were fully busy ingesting data. But that's not always going to be the case. Usually you've got records coming in, and so you're allocating a new column for each record. And so therefore every record is in the same shard, and you're only ingesting to maybe a couple shards at a time if you're batching things up a little bit. And you could get fancy and allocate records into different shards to distribute load. And we're starting to experiment with that a little bit, but you can get pretty high rates of ingests. Like that 300 gigabytes of taxi data that comes in as CSV files that are stored on S3. And we were able to download and index them in like less than 2 hours. So, I mean, that's not like blazing fast, but it's pretty doable. So it definitely depends on your data, and there's still a lot of optimization that we have to do and benchmarking that we have to do to be able to answer those questions better.
I was just thinking about that because you mentioned support for time series data and higher resolution timestamps.
Yeah, and unfortunately, that would sort of kill the ingesting into multiple shards at the same time thing, because the assumption we would make there is that columns are ingested in time order. And so you can jump around from shard to shard when you're doing ingest without some, higher level logic on top of that, which would probably be pretty confusing. But I don't know. I mean, maybe we would be able to make it fast enough, with a little bit of batching and in terms of the import, and it would be okay. I'm not sure.
One other thing you mentioned was that you allocate data to shards based on a hash, and I don't remember used a particular adjective to describe the hash. I don't know what it was, but you get a choice over which fields that's hashed. Is it hashed over the entire data? And does that let you play any kind of games at query time where you can tell by the hash maybe what shards it's in? Kind of like Cassandra does, a partition lookup based on the hash. It knows which nodes essentially have that data to look it up.
Yeah, so the hash is let's see. So you're taking a column ID and you're saying which shard is this? Sorry, a column ID is basically a record ID, and you're saying which shard does this go into? And that's basically, you're just dividing it by 2 to the 20, a million. And so based on that shard, you hash that shard into what we call a partition. And so by default, there's 256 partitions. And so those partitions actually get mapped onto the nodes, and that's what allows resizing. So you would move whole partitions from node to node when you do resizing. But so there's another hash that maps the partition onto the node, and that's it does it in some way that is sort of like optimized for when you resize the cluster. It has to move the least amount of data around. But on the query side, so if you're doing a point lookup, yes, you could definitely figure out which node had that data, but you really never want to do that in Pilosa.
Yeah.
You're almost always doing like segmentation queries where you're saying, give me all the records that match these criteria. And so then you want to look at all shards to see if they match those criteria. Or you're doing group bys or counts or roll-ups, something that takes the whole data set into account, after filtering. Queries almost always get fanned out to every single shard. And then, some shards don't have any data, that's fine, that match the query. And then insertions do go to the node that has the shard that needs to insert that data.
Thank you.
Yeah, thanks for your questions.
So I just wanted to say thanks again to Matt for taking his time to present to us tonight. I really enjoyed it. I expected I would, and I did. So he didn't disappoint. This will be on YouTube. We will send out a link so everybody can watch again. And I know I have one question for Matt that I haven't quite formulated yet, so I'm going to reach out to him over email. But it looks like he, at the end of his slides, also was kind enough to give his email address if people have questions going forward. So we will definitely keep in touch with him, and especially if there's anybody who thinks that they could use Pilosa in their organization. I'm sure he would be very interested in hearing from them. I don't know if you want to take a second, Matt, and tell us any good news about funding.
I've been saying this forever, but I think there's going to be an announcement like this week.
Okay.
But basically, we're funded for at least the next year or so, and we're sort of trying to get on a path of sustainability. So if your organization has any interest in using Pilosa, we would definitely like to talk to you. We're trying to stand up sort of a cloud managed services offering, which should make it a lot easier to use. But if you want to use the community edition, or you want to get an enterprise license and a support agreement and all that, we're happy to help you either way. We believe in investing in the open source community, as well as at least trying to make a sustainable amount of money doing this. So yeah, any questions about Pilosa, or if you want any help using it or whatever, definitely don't hesitate to reach out to me, either via email or Twitter or on the Gopher Slack. I think I'm just Jaffe, Jaffe@pilosa.com, Matt Jaffe on Twitter.
I didn't mean to put you on the spot. I thought I was hoping that there would be the opportunity for you to brag about. And I thought, honestly, I thought that there was, but I guess I mistook the Oracle thing for.
So the Oracle thing was not funding, but we were a member of their startup accelerator program, which means that we get some free office space with them, and basically access to all their cloud and cloud credits and that sort of thing. And so that's been kind of a cool partnership to sort of accelerate, our growth and our ability to sell into the enterprise.
Cool. Well, thanks again, Matt, and we'll look forward to. I'm looking forward to some good news. I know it's going to happen, so I'm not worried about it. Just a matter of time, as they say. And and thanks again for taking time on a Tuesday to talk to us.
Hey, thank you for having me. Happy to do it anytime. It's always fun. It's good to meet everybody.
Yeah. All right, we'll talk to you soon then. Thanks again.
All right, see ya.
Have a great night.